Now in this video, the last video we were evaluating a definite integral using the fundamental theorem of calculus. In this video, I'm going to run through a lot more problems, and I'm also going to solve things given a certain notation. Okay, so basically just some example problems you guys can follow along, and also I'm going to use some shortcuts, some notation. If you get lost, be sure to go back and understand how I'm doing the antiderivatives. That's probably where I'm losing you, is I'm going to be doing the antiderivatives a little bit quicker in this video, just so that I can work through more problems in a smaller amount of time. So basically, all I'm going to be doing here is just evaluating definite integrals. Evaluating definite integrals, and this is the example version. So example 1. Now these examples have a little bit of variety in them, not too terribly much, a little bit of variety, just so that you guys can get an idea as to what is going on. So basically in each one of these examples I'm evaluating various integrals. So I'm going from 2 to 1 in this case of x squared minus 3 dx. Now the first thing I need to do is evaluate this antiderivative, figure out what the antiderivative of this thing is. Now hopefully you guys can do this really quickly, so I can rewrite it, I can integrate it, I can simplify it. Basically this one just becomes, I'm going to go ahead and write it in this term, right, in these square brackets. So the antiderivative of x squared is x cubed divided by 3. So once again, this is x to the n plus 1 divided by n plus 1. In this case, n is going to be equal to 2 minus 3. And in this case, if I do the x to the n plus 1 divided by n plus 1, where x is 0, I just end up with 3x. Now what happened to the limits here? These are very important numbers from 2 to 1. Right? The bigger the limit is, the bigger your area is going to be ideally. So here you end up with, I write my limits over here. And this is just another notation thing so that I can quickly understand that, hey, I still haven't plugged in my limits, my endpoints, to figure out what my value is going to be. Okay, so first thing I need to do is plug in my 2. Okay, so then this is just going to be equal to, I get 2 cubed divided by 3 minus 3 times 2. So that's my one endpoint. In this case, it's my right endpoint. And then I'm just subtracting my left endpoint, right, my lower endpoint. And so then I get 1 cubed divided by 3 minus 3 times 1. And when I calculate this out, I get 8 over 3 minus 6 minus 1 over 3 minus 3. Do some mental math here, or I can simplify it a little bit. Basically, I just end up with minus 2/3. Okay, example 2. I'm not going to spend too much more time on example 1. Pretty straightforward. Example 2. Another indefinite integral we're trying to calculate. So this time it's going from 4 to 1, 3 root x dx. Now I'm going to rewrite this thing before I even start doing the antiderivative, because as you guys know, I'm starting to get a little bit anxious, starting to get a little bit nervous about this. So the integral from 4 to 1 of 3 x to the 1/2 power, that dx. Now it's an x to the 1/2 power. I'm feeling a little bit better. Now I can actually do what the antiderivative is asked, or I can take the antiderivative of this. So the 3, that's a constant out front, that's just coming along for the ride. And so I'm going to end up with x to the n plus 1 divided by n plus 1. So in this case, my n is 1/2, so I end up with x 1/2 plus 1 is just going to be 3/2 divided by 3/2. And of course, my limits, I've got to make sure I'm going from 4 to 1. Now before I plug in the limits, I'm going to simplify this a little bit. So the 3/2 I can basically flip, so I get 3 times, instead of 3/2 on the bottom, I can say 2/3 up top to the times x to the 3/2 power. Still square brackets, 4 to 1, and then a 3 and a 3 cancel out, and I just end up with the fully sort of simplified form before I start plugging my endpoints. I end up with just 2 to the x, or 2x to the 3/2 from 4 to 1. Now from here, I'm sitting pretty well. All I need to do is plug in these endpoints and I'm done. Remember, I'm going to plug in the top one first. So I get, it's going to be equal to 2. Instead of x to the 3 halves, in this case, I've got 4 raised to the 3 halves power. Okay, so that's my first one. Now my second one is I'm just doing the same thing, but I'm plugging 1 in. So I'm subtracting the 2. 2 times 1 raised to the 3 halves power. Okay. Now 4 to the 3 halves power, you guys should be able to do stuff like this in your head. So anytime something is divided by 2, you can take the thing and basically take the square root. So the square root of 4 is 2. That gets rid of the half. And then 2 cubed is going to be 8. And then 8 times 2 is going to be 16. So this first term just becomes 16 minus. In the second term, of course, 1 square root of 1 is just 1. 1 cubed is just 1. This one just becomes 16 minus 2, which is going to be equal to 14. Just like that. Look at how much space that took, even though most of it I was rewriting these integrals just to make them a little bit more simple, or just to simplify them to make them a little bit more understandable. Just like that. 14. Way, way simpler, way, way easier than using sigma notation, than using limits as n goes to infinity. However, once again, that is important stuff to know. So last example I've got for us, example 3. So we did one with a simple power rule. Example 1, we did one with a little bit more complicated power rule. This one we're going to jump into some trig stuff. Now once again, trig stuff is important. You might be groaning a little bit, but trig stuff is important because it shows up all the time in real world applications. Okay, so this one I'm going to evaluate from pi over 4, groan, need to know the unit circle. Don't groan, know the unit circle, just make it happen. Secant squared of x dot dx. Now secant squared, this is already sort of simplified and rewritten. All I need to do is just look up on my table secant squared, or remember that the derivative of tangent is secant squared. And since I'm going backwards, the antiderivative of secant squared is just going to be the tangent. So I can say the tangent of x from pi over 4 to 0. Now I'm just plugging in my endpoints, right? So I can say the tangent of pi over 4 minus the tangent of 0. Now that's going to be my answer. So the tangent of pi over 4 is just going to be 1 here. Tangent of 0 is equal to 0. Once again, if you know your unit circle, this problem is super, super easy. So 1 minus 0 is just going to be equal to 1. So a couple example problems. Look at how little space that took, even though it was a trig function, even though you guys were a little bit worried about it, not a problem. Just solving the problem and moving forward. Okay? Just because I knew my unit circle, just because I knew that secant squared, well, antiderivative was tangent, or derivative of tangent was secant squared. Okay, guys, see you next video.